Assalamualaikum warahmatullahi wabarakatuh. Good day everyone.
Waalaikumsalam doktor.
Selamat tengah hari. Sehat-sehat semua ya.
Alhamdulillah.
Ya, kita jaga kita ya. Jangan sampai ada yang terinfeksi. Oke, kita melanjutkan transistor ya, Mosfet, metal oxide semiconductor transistor, field effect transistor. Okay, I will share whiteboard.
Yes, doctor.
Okay, so I will draw about the Mosfet, metal oxide semiconductor field effect transistor. Okay, at the Mosfet we have semiconductor. Yeah. Anyone join? Okay. So this is a P-type, yeah. And we have a P-type semiconductor, and then on top of this we have oxide, yeah, silicon dioxide, for example. This is silicon dioxide, yeah. And then on top of this we have a metal, yeah, or conductor, yeah. And then in the shallow dip in the left we have N-type, yeah. We fabricate the N-type in the P semiconductor, yeah, heavily doped, yeah, N-type. And then on the right side, so we have a heavily doped N-type as well, yeah. And then on top of this, we have a metal, yeah, as a conductor to connect N-type, yeah. So this we have three terminal, yeah. Anyone join? Okay. So at the left terminal we have a source, and the right terminal we have a D, yeah, drain, and then we have a G in the middle, yeah. And then we on the bottom we have a body, yeah, or the base, yeah, B. So usually S and B is grounded. So we have this is a ground. And B also grounding, yeah. So we have discussed regarding with the how the channel region, yeah, in the middle here is the this is a channel, yeah, channel region. This is a channel region, yeah. So when we apply the voltage, yeah, GS, yeah, positive, yeah, this is a positive. So we will push the holes to the bottom, yeah, to the B, so then we can have a in this region we create the channel region, yeah. So when we apply voltage, yeah, into the D, yeah, DS, yeah, DS, so we have a DS like this. then there will be created the voltage, the current flow, yeah, from the D to the S here, or electron flow to the from the S to the D here. Yeah. So when uh, the channel region created, yeah, the channel region is in this. Yeah. So initially, yeah, we increase the DS. Yeah, the channel region created like this one, and then like this one. Yeah. So then this is the creation of the channel region. Channel region, and then we can have a electron flow here. Okay. So we can say, yeah, yeah, if gate uh, voltage, yeah, gate voltage is VGS, yeah, VGS. This is gate voltage. Yeah, we keep the positive, yeah, in the terminal G, so then will be push, yeah, the hole to the bottom, and then we create the channel region. Yeah, so the hole cannot move here, from the G cannot move here because of the insulation. So this is the remember SiO2. Yeah, this is okay. So if the gate voltage VGS, yeah, is above uh, threshold voltage, yeah, where VGS greater than or equal to threshold voltage VT, then will create the channel region. Okay, so if VDS, yeah, VDS this one, VDS, yeah, this one, VDS. This is a VDS, yeah. So this is a VGS, yeah. If VDS is sorry, if VDS is below overdrive voltage, yeah, yeah, where the overdrive voltage is the VGS minus VT. So this is a overdrive voltage. Yeah. So in this case, the variable resistor happen between uh, D and S. Yeah, between this is between D and S. Yeah, this is the variable resistor. Yeah, we know increasing the DS with the we have last time. Yeah, yeah, IV. Yeah, so this is increase. Yeah, so this is like a resistor. Yeah, increasing voltage, increase the current. So this is the have the variable resistor there. Okay. So where VDS uh, yeah, less than VGS minus VT. Yeah. If VGS minus VT is overdrive voltage. If less than VDS, less than VGS and VT minus VT, so then there will be a variable resistor. Yeah. So the variable resistor in this region. So this is maximum. If this is a overdrive voltage, this is maximum. So then will be and then the no more increase the current when you increase the VDS. Okay, so in this case, yeah, so we have a variable resistor. Yeah. So in this case, yeah, variable resistor happen if VGS greater than VT. Okay, and uh, VDS greater than 0 and smaller than the VGS minus VT. Yeah. So this case, VGS minus VT is a overdrive voltage. So in this case, yeah, the VGS control uh, the area of the channel. Yeah. So remember here, yeah. So if we apply VGS, yeah, then you can see, yeah, the depletion region here, yeah, will be created. Yeah, actually, there is no hole. Hole will be pushed down. So then will be increase the area here, the area of the channel region. Yeah. So increasing the VGS will increase the channel region area. So increasing the channel region area will allow the current, yeah, greater to flow, or electron to flow from S to D. Okay, so VGS control the area of the channel in this case. Yeah, and then we have as we have read in the previous class, the conductance. Yeah, D to source, yeah, is GDS equal yeah 1 over RDS. This is R is a resistance equal 1 over sorry, not 1 over, this equal to Kn, yeah, VGS minus VT minus half VDS, yeah, half because this is we have the from S to drain, so that we have half here, and then uh, we have also the current, yeah. Yeah, we have written also in the past uh, current D to S, yeah. So it's just ID equal Kn VGS minus VT minus half of VDS multiplied by uh, VDS, yeah. So this is the ID. Yeah, ID is the current from the D to S. So this is we have ID. Hmm. So when we plot, yeah, plotting, yeah, of IDS and 3DS. So this is almost straight, yeah, line. So we have ID, DS, PDS here. It's almost straight line. Yeah, it's straight, yeah, straight line. So where the maximum here is the, yeah, this is equal to VOP. So this is the plotting of IDS VDS, where the in this case VDS equal to VOV, so there are no more increase the current, yeah, IDS. If we plot, yeah, completely, yeah, if we plot completely, yeah. So in this case, POP, yeah, in this VDS equal the POP, yeah, at a certain VGS. So in the plotting complete, we have ID, yeah, and this is the VDS, and the voltage is the for example milliampere, yeah. So we have uh, at the uh, for example, yeah, if VGS 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 equal or less than 50, what happen, is there any current? If VGS less than threshold voltage, yeah, there is no current. Am I right? So this is the VGS less than 50. So this is we have this. This is this we have VGS equal or less than VT. Yeah. So if we have here, yeah, VGS VGS, this one is less than the threshold voltage. Threshold voltage means the creation of the region. Yeah, threshold voltage is the minimum of the VGS that creates channel region. Yeah, so if VGS is equal 50 or less, so then will be no current flow. Yeah, there is no current flow. Yeah, in this D to S. Yeah, there is no ID equal 0. So if VGS equal or less than 50, yeah, so then the ID equal 0. Yeah. So here we will make this is a VGS less than or equal with the threshold voltage. So what happened when we have a VT, yeah, VT, sorry, VGS increase. We increase the VGS, so then VGS uh, equal, for example, VT threshold voltage plus, for example, 0.5 volt, for example. For example, yeah. So then there will be at a set. Uh, so we have this one, and then we have
Prof,
ya,
ada yang nak masuk?
nak masuk. Okay. So in this case, we have yeah, threshold voltage, yeah, in this area. Yeah, so this is a threshold voltage. Yeah, and then will have no more increase. Yeah, so this is the if we have VD, yeah, VDS more than VGS minus VT, yeah, VGS minus VT, yeah, 0.5. So this will be saturation. Okay. So when we increase again the VG as equal VG plus 1, for example, 1.01. So we have another graph. this one. Yeah, so this is we have a linear increase and then saturated. Yeah, saturation. And then again we have another VGS. We have VGS equal VT plus 1.54, for example. And then we have another VGS plus equal VT plus 2.04, for example. So then we have here, when we operate the transistor, in the linear operation, so we have we call this is a triode mode. We have last time. And so this in this case, we have a triode. And then from the triode, so we have another operation here is a saturation mode. Remember, and PJT also happens. And then if we have the VGS equal VT and less than VT as well, so there will be zero. So this is we call as a cut off. Cut off mode. So this is we have for three mode of the operation of the transistor. For the Mosfet. In triode, saturation, and cut off mode. For the VGS VT plus 2 volt. In this graph we will use this one. But for the VGS VT plus 1.5 volt, so this is in this graph, for example. So then we have a border here, between triode mode and saturation mode. We have this point, this point, this point, this point, this point. So we have this is this is the border, between triode and the saturation. So this is the in the triode mode. In the triode mode. In the triode mode, we have a VDS, less than or equal to VGS minus VT. But for saturation, saturation, where the VDS, greater or equal to the VGS minus VT. So this is the saturation mode. How can the saturation mode happen? Remember, remember when we change the VGS, changing VGS, remember, will create the channel region area. Region area. So this area will allow a certain number of electron to move from source to drain. So the number of electron limited to the channel region. The channel region will limit the moving of the current to flow or moving of electron to flow. So that's why this is will be saturation. But when VDS is less than VGS minus threshold voltage, so we have a linear operation. So increase the current until all of the electron flow in the channel area, channel region area. So the area of VGS VT plus 2 volt is greater than the channel area, from VGS equal VT plus 1.54, extra. So this is why the saturation happen. Remember, in the BJT or in the FET yeah, transistor. So we also having the uh, triode mode, saturation mode, and a cutoff mode, yeah, of the operation of the transistor. Okay. So in this case, yeah, in saturation, yeah, mode, yeah, the ID, yeah, ID equal, yeah, to the VOV, yeah, happen in the VOV, yeah, overdrive voltage. So in this case, the ID equal the uh, of overdrive voltage happen in the half of Kn, yeah, VOV square. Yeah. So this is ID, and then equal to the half of Kn VGS minus VT, yeah, square, yeah, VOV is a VGS minus VT. So in this case, yeah, uh, we have yeah, uh, three region, yeah, in the transistor operation. The first triode region, yeah. So the triode region is the this one, yeah, dash line left. The left of dash line is the triode mode, and the saturation region is the right side of the from the dash line, yeah, and the cutoff mode is in the VTS line, yeah, yeah. IDS is 0. So we have a three region. Yeah, we have a saturation region, and then the third one is the cutoff region. Yeah? Or we can have mode of the operation of the transistor. Sorry, and then we have uh, here. What is the Kn actually? Yeah, with the what is the Kn? The Kn we have question. What is the Kn? Yeah. So uh, introduce, yeah, the Kn because of the introduce the electron mobility in the channel. Yeah. So electron mobility is a mu a. Yeah? And then uh, the second one, from this phenomena, so we have introduce introduce the oxide, yeah, oxide capacitance, yeah, oxide capacitance, or we have a COX, yeah. So this happened because we applied the uh, uh, VGS, yeah, as positive voltage. So when we apply the VGS positive voltage, yeah, then uh, capacitance is created, yeah, between channel and gate, yeah, between gate and channel, yeah. So in this case we call as oxide capacitance, COX. So this is the again we see in the Mosfet. Yeah. So when we create, we apply the G here. So we push the hole, yeah, to the bottom, and then we create the channel region. Yeah, creation of the channel region. Yeah, we know that will allow the mobility of electron move from the yeah S, yeah, from the source, yeah, uh, heavily doped N in the source to the heavily doped N in the drain. So we create the channel region. The creation of the channel region, therefore, will allow the creation of the capacitance in here, yeah, or we call as an oxide capacitance. We know that the capacitance is uh, 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 the measure, yeah, how the capacitance can store, yeah, the electrons there, yeah, or how many electron can flow, how many electron can be stored, yeah, in this capacitance, yeah. So that this is the creation of the Kn, yeah, Kn because of the mobility of electron, and the second is because of the creation of the oxide capacitance. Uh, and then the third one, yeah. So in this case, yeah, we can say that the more capacitance, yeah, of the COX, meaning that the more electric, yeah, yeah, electric charges, yeah, electric charges, yeah, when uh, applied voltage increase, yeah, is increase. Uh, the third factor that the creation of the Kn, yeah, is the introduce of a geometry, yeah, of the, or we call as the aspect ratio. Aspect ratio between uh, W and L, yeah. Uh, so we call as W over L is the aspect ratio of a transistor. Yeah. So the aspect ratio, we know that this transistor has a dimension. Yeah. For example, yeah, we have the weight and the width. Yeah, and the we have one. This is a, yeah, P type of semiconductor. This is P, and then this is heavily doped N source, heavily doped N drain, and then we have here as a this is a length. Yeah, this is length, and then we have width. Yeah, width here W. So yeah, the width of the capacitor, yeah, sorry, transistor, and then the length of the channel region. So this is the aspect ratio of the transistor. Okay, yeah. From this three introduces of mobility and oxide capacitance and aspect ratio of the transistor, so that we can get the uh, Kn. Yeah? So we call as a, yeah, the conductance uh, coefficient. Kn. Yeah, so this is conductance coefficient we call as a Kn. Yeah, so this Kn is a proportional. Yeah? Proportional to to each of those on this factor introduced. Mobility of electron, then the oxide the capacitance, and the aspect ratio of a transistor. So we have Kn then equal or same as mobility of electron, COX, and the W over L. So this is the unit of the ampere over square voltage. So this is the Kn. Kn is dependence of the mobility of electron, capacitance, and the dimension of the transistor, aspect ratio of the transistor. So this is all of the characteristic of the material, right? The mobility of electron is different from one material to another material. In the germanium, silicon, or gallium arsenide, they will be having their own mobility of electron, as well as the capacitance. Oxide capacitance also have a different value. Different constant. This is as constant. This is as constant. This is constant. Constant. So this is a Kn as a conductance coefficient is the constant as well. Dependence of the dependence of the material. Okay. So this is the Kn. So then therefore so we can have the application of the usage of Mosfet. Yeah. Yeah. So we use the Mosfet as an amplifier. Amplifier. And its saturation mode. So in saturation mode, so this is as an amplifier. Remember in the BJT as a transistor as an amplifier as well. In the MOSFET saturation mode as an amplifier. In BJT saturation mode as an amplifier. In MOSFET in FET or BJT, so we have a saturation mode as an amplifier. So another application for digital application. So we switch the transistor. We set it between the on and the off states. So in this case, that is the in cut off mode. This is as a off, and triode mode, as a on. Okay. So we can have if we controlling the VGS and VDS, so we can make the in the digital application on and off. We know that the on off is very important in the digital in binary, on off, so we can have the information with the in the cut off mode and the triode mode. So this is as a continual, so we can have digital in the digital application, also as an amplifier, so we can amplify the current, dependence of the VGS, the operation, at a certain VDS. Okay. Then we have the illustration. Yeah. In the for this Mosfet, voltage to current, amplifier. So the illustration, we know that the symbol of Mosfet is like this one. Between G, this is G, this is G, and this is D. So we have this is a gap between G and D. There is a gap here because of the silicon dioxide, oxide. And the D, and then we have a S here, and another side. So we have a this is R. If we connect with the resistance in gate G, and then we have this is the voltage, and then we have a ground here. So this is we have a VG. So we apply G and the positive, and the D here, is a drain where the high potential, and then we have a VDS here, VDS. Of course, this is variable. This is also variable, and then we have this is as a we grounding. This is as also we grounding. So when we apply voltage, this one, this is apply the voltage, so then we will create the threshold voltage. Am I right? So the threshold voltage will allow the current to flow. Current to flow. This is ID. This is a so this voltage, this voltage will control this current. So this voltage control this current. So Vg will control the current. Remember in the previous figure, this one, right? So if we apply the VGS here, VGS, then we create the channel region, and then when we apply the voltage VDS, so they will current IDS will flow from D to S, or electron flow from S to D. Same. So how big this current depends of the big of the VGS applied. So then that's why this we control the current, and then this, right. So this is if we have a VGS, same as a threshold voltage, so the current or VGS less than threshold voltage, so the current ID is 0. But when a certain VGS plus 50 plus something, for example 0.5 volt, so there will be we have a certain value of a current here, and then we have another current with another VGS, another current, another VGS in saturation. This is okay, a different current. So that's why we call the VGS control the VDS. And that's why the VGS is control the VDS. This voltage VGS control IDS. Yeah, so a voltage control the current. Yeah. So then we can keep the summary of this of the Mosfet. Yeah, we can keep the summary. Yeah. We have a characteristic of Mosfet. Yeah. One. Yeah. Conductance coefficient. Kn equal mobility of electron and the oxide capacitance and the uh, aspect ratio of the transistor. And then the second one is the threshold voltage. Yeah, so the MOSFET we should have the what is the threshold voltage and then Kn. So by determining the VGS and VDS, so then if VGS less than VT, yeah, threshold voltage, so we have a cut off. This ya. Cut off and ID equal 0, ya, 0 ampere. So other ya, that overdrive voltage equal VGS minus VT, ya, or greater than that one. So then if VDS less than VOB overdrive voltage, then we operate yeah uh, then we operate as a triode mode. Hmm. Another, yeah, where the VDS greater than or same as VOB overdrive voltage, we have the saturation mode. Yeah. So then we have in a triode mode. Yeah, we have in triode mode we have ID equal half Kn uh, VOV square. Yeah. So this is the yeah, this is a S function of VGS, yeah, as we have explained before. Yeah. Okay. So this is the end of this MOSFET. Yeah, so we have study up to now about the yeah, we have a PGT, yeah, we have a FET, we have a MOSFET, yeah, or we have uh, a PNP, yeah, uh, transistor, heavily the PNP transistor. So we have for at the up to now also the we have introduced the symbol of semiconductor devices diode. Yeah. So diode, there is the for the rectifier, or we have a diode for the uh, s- for the limit the voltage. Yeah. So this is the uh, uh, we have up to now uh, we have five semiconductor devices, yeah, that we can fabricate, yeah, on the silicon wafer, yeah, in nano order, nano order. So we know that like nowadays, what is that, semiconductor chip, yeah, or we have microchip, yeah, micro chip, yeah, yeah. So we have i7, yeah, and we have i5, etc. So there are a million of transistor there, yeah, because of the technology of miniaturization, yeah, technology, yeah, nanotechnology. So then we can fabricate BJT, FET, MOSFET, heavily doped NP transistor diode, yeah, and a small scale, yeah, of the transistor. So then we can increase the capacity of the microprocessor, and then we can increase the function of the computer, yeah, to compute, yeah, yeah, as for the yeah, any purposes, yeah, for the gaming, for the programming, yeah, for the calculating, etc. Okay, so this is the end of this class. So I hope you get the very easy understanding, yeah, and then you are ready for later, yeah, for working in semiconductor, yeah, in Intel, yeah, for example, yeah. And some many of friend of you, yeah, working in Intel, yeah, and other semiconductor. Of course, this is the offering the higher salary, yeah, than average. Yeah, yeah. Instead of the working in the oil and gas, so working in the semiconductor, yeah, offering the high salary. Yeah. Okay. Any question? Any question regarding the MOSFET? Uh, next, we have another semiconductor devices like MOSFET. Okay, brother, sister, any question?
No, Doctor.
Okay, yeah. If you have no any question, so I end this class. Ya, tetap kita jaga kita, ya, jaga kesehatan. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor. Salam.
Oke,
Tinggal tuh.
oke.